Hello, today we're going to talk about the high voltage direct current systems. This is a kind of system that we actually see a lot in the world today. I'm going to tell you a bit more about it. I'm going to tell you about its history, its design. I'm going to tell you about the components that it has, its advantages, and also the installations that we see around the world with this kind of system. What we have in here for the history, we all know that the first commercial electricity generated by Thomas Alva Edison was direct current electrical power. But well, as this direct current voltage could not be transmitted over long distances as was needed, they started transmitting alternating current voltage. But over the years, this changed with the development of high voltage valves. I'm talking a bit about its design. Well, the fundamental process that occurs in an HVDC system is the conversion of electrical current from AC to DC at the transmitting end. This happens with a rectifier, and it goes the other way around at the receiving end. It goes from the DC to AC, and it's gonna happen with an inverter. I'm gonna show you three ways of achieving this conversion. We have the natural commutated converters, we also have the capacitor commutated converters, and we also have the forced commutated converters. Well, we're gonna start with the natural commutated converters. These ones are actually the most used in the high voltage direct current systems that we see today, and the thyristor is the main component that enables this conversion. This component can actually carry very high currents, up to 4,000 amperes, and it is able to block very high voltages as well, up to 10 kilovolts. Also, by connecting the thyristors in series, it is possible to build a valve which can block higher amounts of volts, and by means of the control angle that we know that the thyristor has, it's possible to change the DC voltage level. Also, for the capacitor commutated converters, these converters are characterized mainly by the use of commutation capacitors that are inserted in series between the converter transformers and the thyristor valve that we were talking about, and they actually improve the commutation failure performances of the converters when connected to weak networks. For the forced commutated converters, these are built with semiconductors with the ability to turn on and off, and they are commonly known as voltage source converters. When it is used with a PWM, it is possible to create any phase, any angle, or any amplitude that you need, and it can be done almost instantaneously. For the components that this kind of system has, we have three main subcomponents. They are the converters that we were just talking about. They are the ones located, as I was telling you before, at the transmission and receiving ends. We also have the transmission medium. This is mainly the medium with which we transmit from one point to another the electricity, the voltage, and everything that we need. And also we have the electrodes. These are the ones used to make contact with the non-metallic part of the transmitting cables. I will tell you a bit more about it in a minute. Well, for the converter station, first we can see it in here on the right part of the slide. Well, it contains multiple elements. We do have the thyristor valves that I was telling you about before, the ones that are formed, that are created by putting multiple thyristors in series. Also, we have the voltage source converters that I was also telling you about before. They are the ones that are built with semiconductors with the ability to turn on and off, right? We have the transformers that we have not talked about yet. They actually have they have the ability to adapt the AC voltage level to the DC voltage level, and they contribute to the commutation reactance. We as well have the AC filters that we see on the image. These ones limit the amount of harmonics to the level required by the network. We know that each network requires a different level of it, so it can be adjusted for it to limit it to your needs. We also have the DC filters. These ones are actually used to reduce the disturbances that are created by the high voltage direct current converters. Well, for the transmission medium, we do have two kinds of transmission. We have overland transmission, and we also have submarine transmission. That it's actually the most common one for high voltage direct current. And for overland transmission, the most common medium used is the overhead line, and it is normally bipolar. This means that the current can go both ways. This is one of the advantages that it has, but I will tell you a bit more about it in a minute. Well, the most common types of cables are the solid ones. They are actually more economic than the oil-filled ones, and there is no length limitation. But when we talk about the oil-filled ones, there actually is a limitation regarding the length of it. It can only go up to 60 kilometers, and they can both go to depths of about 1,000 meters. This is when we're talking about submarine transmission. Well, for the electrodes, that it's the last part of it, they are mainly the ending tips of the cables that transmit the electricity. We know that the cable is usually covered in non-metallic elements, as I was telling you before, such as the oil-filled one, and they are the ones in charge of being the contact point for the voltage and current to flow. Well, we also have quite a few advantages for this kind of transmission system. The first one of them would be the better cost-benefit ratio. I will show you a graphic in a minute so that you can understand it a bit better. We also have, well, we actually don't have any limits in transmitted distance, and this is actually valid for both overhead lines and sea or underground cables. Also, the direction of power flow can be changed very quickly. As I was telling you before, these cables are usually bipolar, so they can be changed very quickly and very easily. For the we do have high availability and reliability rate. It is actually shown by more than 30 years of operation. Also, the native right-of-way is much smaller for HVDC than for HVAC, and therefore the environmental impact is way smaller, which is very important nowadays. And lastly, we do have that it has a very fast control of power flow, which means that we have more stability not only for the HVDC system, but for the surrounding AC system as well. Well, this is the image that I was telling you about. You can see in here the comparison between the AC price and the DC price when it comes to longer distances. The longer the distances, we see that the DC price becomes more affordable, becomes more economic than when we compare it to the AC price. So let's say that when it comes to a distance over 700 kilometers, well, it becomes way more affordable, the DC price, as we see. That's one of the reasons why it's becoming so popular lately. And well, we also have the installations around the world to close this presentation. We do have three very important installations. These are ones of the biggest installations that we currently have in the world for HVDC systems. First of all, we have the one in Itaipu, Brazil. This one was chosen to supply 50 Hz power into a 60 Hz system and to economically transmit large amount of hydropower over large distances. This actually has a length of overhead line of 800 kilometers and a power of rating of 3,150 megawatts. We have the one in Leyte, Luzon, Philippines. This one was chosen to enable supply of bulk geothermal power across an island interconnection and to improve stability to the Manila AC network. This one has a length overhead line of 430 kilometers and a length of submarine cable of 21 kilometers. Overall, it has a power rating of 440 megawatts. And lastly, we have the one in Queensland, Australia. This one was chosen to interconnect two independent grids to enable electricity trading between the two systems and to ensure very low environmental impact, reducing construction time as well. This one has a length of DC cable of 65 kilometers and it has a power rating of 180 megavolt amperes. Well, this was pretty much it for today's presentation. I hope you enjoyed it. I hope you learned a little bit more about it, and thank you so much for watching it.